Alright, so in this video, I'm gonna be explaining another important article with the title Margin-Based Adversarial Learning for Domain Generalization. The name of their model is MADG. So this paper in 2023, domain generalization techniques have emerged as a popular approach to address the challenges of domain shift in deep learning, with the goal of generalizing well to the target domain unseen during training. In recent years, numerous methods have been proposed to address the domain generalization setting, among which one popular approach, which is adversarial learning-based methodology. The main idea behind adversarial domain generalization methods is to learn domain invariant features by minimizing discrepancy metric. However, most adversarial domain generalization methods use 0-1 loss based H delta H divergence metric. In contrast, the margin loss based discrepancy metric has the following advantages: more informative, tighter, practical, and effectively optimizable. To mitigate this gap, this work proposes a novel adversarial learning domain generalization algorithm, MADG, motivated by margin loss based discrepancy metric. The proposed model learns domain invariant features across all source domains and uses adversarial training to generalize well to the unseen target domain. We also provide a theoretical analysis of the proposed MADG model based on the unseen target error bound. Specifically, we construct a link between the source and unseen domains in the real valued hypothesis space and derive the generalization bound using margin loss and Rademacher complexity. So we have a set of domains, and we use X and Y to refer to a label sample. The expected error rate of a classifier with respect to a distribution is just expectation of the indicator when they don't agree with each other. So we define the margin and the corresponding margin loss. So half of f of x y minus maximum of f of x and y prime. So the error is just the expectation of phi compose. We have composition with row. We have defined row, and the composition works like this. If row is less than t, then it's 0. It's between 0 and row, then it's just a linear function. The margin disparity in its empirical version are defined like this. This is the margin disparity. And f and f prime here, f prime, there are different scoring functions. Margin disparity discrepancy is used to quantify the degree of discrepancy, or let's say disagreement, between decision boundaries of classifiers using their margins, trained on different domains. Such a measure can be used to evaluate the generalization performance of a model across multiple domains. The MDD and its empirical versions are defined in these two equations. So we use these above terminologies, which however focused on domain adaptation and handling multiple seen domains and unseen target domain is non-trivial. So you see in this picture, the space of intersection, which is in yellow in MDD, is reduced as compared to 0-1 loss, which is blue. So such a margin-based approach has 4 advantages. The first advantage is that they are informative. Generalization bounds based on margin loss for classification provides more information than just 0-1 loss. And the second advantage is tightness. In contrast to using a 0-1 loss to identify samples causing disagreement between classifiers, margin loss computes disagreement between scoring functions using the smooth function. The third advantage is that we have classifier-aware discrepancy. MDD considers the classifier function while measuring discrepancy. And finally, the last advantage is the efficient optimization and practicality, because the equation 5 only requires taking the supremum over one hypothesis. So we begin by considering a setting where training data consists of n number of S-1 labeled source domains and a single labeled source domain and a single unlabeled source domain, and show an upper bound on error in this setting. So the difference between these two domains is upper bounded by this. And consider a scoring function f, unlabeled source domain d sub st, which is here, and a mixture of ns source distributions. So d sub s bar is just d of s sub bar is just a linear combination of source domains, and this one is just a mixture of coefficient. Then we have this error on the unlabeled source. And they have this lemma for theorem 2, because this lemma says if the difference between s sub I and this s sub k is less than a threshold epsilon, then for any I and k and f be a scoring function, then the following equality holds for MMD between any pair of domains. It's a very strong conclusion, because it says for any pair of domains you can have this bounds. So now the theorem says consider mixture of ns source distributions, scoring function f, unseen domain, and gamma, where du is the projection onto convex hull of source domains. Then the unseen target error is bounded. So we are always upper bounding the unseen target error. And it also talks about Rademacher complexity. And another generalization bound with high probability, we have this upper bound. So let's go to the algorithm. So as seen in the theorem 3, the unseen target domain error is upper bounded by a convex sum of empirical source domains. So this is how we are using this theorem. Now that we know what are the factors in our upper bound, then we want to minimize two important terms: the convex sum of empirical source domain errors and epsilon hat. So we are working on efficient estimation of epsilon hat. because epsilon hat is just the difference between the distance between these two domains, these two source domains. Is maximum pairwise empirical MDD among all source domains. So we can also interpret this epsilon hat as the upper bound of the empirical MDD between any two domains inside the convex hull. If we minimize the sum of the empirical MDD between the different pairs of the source domain, then the size of the convex hull reduces. Thus, one effective way to estimate epsilon hat is to consider the term below. To find the optimal f in the hypothesis space, we formulate our objective function as a minimization problem. Since empirical MDD is defined as a supremum of the hypothesis space, minimizing it is in turn a minimax game with a strong max player and weak min player. In order to strengthen the min player, we use a feature extractor G. So this is our feature extractor G. So we are minimizing with respect to G as well, because it's our feature extractor. So to solve this minimization problem, we need to design an adversarial learning algorithm whose model architecture is shown in figure 2. One classifier F. So because it's adversarial, we have this generator G and our classifier is F. One classifier F performs the classification task on all source domain, while J other classifiers, let's call them F prime, compute the empirical MDD between different pairs of source domains, which finally sum together as a transfer loss. So to compute the source error in this minimization problem, we use just the standard cross entropy loss. For convenience of optimization, we approximate MDD loss as the d of ds sub I and ds sub k in terms of two loss functions. And we train the feature extractor to minimize the above MDD loss by using a gradient reversal layer. And D is not differentiable with respect to the parameters of F. So this is the margin-based adversarial learning for domain generalization. Once you get your n number of S labeled source domains, you go, so in each epoch you have a batch. For each batch, we go through parameters of F and G. Remember, G is your generator, F is your classifier. So classifier of generator, so this is what you classify here, but we compute it using this approximation. You compute the MDD, which is a good measure, and then we compute the transfer loss that we discussed in the previous slide. So this study presents a novel adversarial algorithm for domain generalization. And it is inspired by the relationship between source and unseen in real value to hypothesis space. We use a margin loss function and Rademacher complexity framework to develop a generalization bound